Assalamualaikum warahmatullahi wabarakatuh. Today's topic falls under external force convection, and then our focus today is parallel flow over flat plate. So, what is the objectives of this subchapter? Okay, when you finish studying this chapter, you should be able, number one, evaluate the convection coefficients in external flow. And then number two, evaluate the heat transfer associated with flow over a flat plate for both laminar and turbulent flow. Okay. So we have a flat plate. Okay, we have a flat plate. And then there is a fluid over the flat plate. Okay, I change the color of this pen. So I take blue. Okay, we have here T infinity that represent temperature for fluid. Okay, and at the flat plate surface, we have T surface, temperature of the surface. And then let's say the Q heat transfer transfer from T infinity to Ts. So this is your Q dot rate of heat transfer. So some of the question, they will not give you the value for the heat transfer coefficient here. So in order for you to determine the heat transfer coefficient for a flat plate, so our focus today is on flat plate. Okay, there is three conditions. Actually, it falls into two major conditions. Okay, the first one is constant temperature. Constant temperature on the surface. And then number two, we have constant heat flux. So under constant surface temperature, it can be divided into two. Okay, first, we want to find local Nusselt number. And then second, we want to find average Nusselt number. And then for the heat flux, normally our objectives on this condition is to find Ts, or you want to find rate of heat transfer, Q dot. Which one? Okay. For the local Nusselt number and average Nusselt number, both of these you may find Q dot, rate of heat transfer. So what is important of you to understand between these two conditions? One, when you're dealing with a constant temperature, you want to find a local Nusselt number and average Nusselt number. So what is important to the Nusselt number? Because from Nusselt number, we can find H. So H is required for you to plug into the value of, into the equation of Q dot H as T infinity minus T surface. Okay, this is equation for convection. Because this topic, this chapter falls on convection. Okay, so our objective is only to find this H. So by using this condition. Okay, after that, we know that the fluid flow over the flat plate have two regions. Okay, it might possess two regions, or it might occurs two regimes. Okay, as we know before in fluid mechanics, we have two types of flow. One is laminar and second is turbulent. So what is important about these two? Because each of these types of flow have different types of equation you have to use in order for you to determine the value of H. Okay, that is what you're gonna learn today. Okay, take a look at this figure. Okay, consider the parallel flow of a fluid over a flat plate of length L in the flow direction. So we have this fluid, okay, flow over a flat plate, and then before it enters a flat plate, this fluid flows at constant velocity and constant temperature, okay, T infinity and V. So what will happen when it approaches to this to the flat plate, and the fluid layer nearest to the flat plate will stick to the surface? This is what we call as no-slip condition. And because when fluid layers stick to the surface, it will affect to the other layers, the adjacent layers. And these layers will increase, the affected layers will be increased as x coordinate increases. Okay? And if we combine all those affected layers, it will create a hypothetical path here. This is what we call as boundary layer. Okay? Boundary layer. Okay, for a flow of turbulence, okay, for a fluid that flows in a turbulent manners, what will happen is actually it will start out with a laminar flow, and then after it reaches or it passes to the critical limit or critical Reynolds number of a flat plate, it will become turbulent flow. Okay, this after it reached to 5 times 10 to the power of 5, this is critical Reynolds number for a flat plate. And after it reached to this level, to this value, it returns into fully turbulent flow. Actually, the turbulent flow starts to happens or start to occur at Reynolds number 1 times 10 to the power of 5. But becomes fully turbulent flow at 3 times 10 to the power of 5. But generally accepted value for the critical Reynolds number for flat plate is 5 times 10 to the power of 5. Okay? And to calculate the Reynolds number here from Reynolds number equation, I believe that everybody already know about the Reynolds number equation, because this Reynolds number equation is already learned in fluid mechanics. But in the heat transfer, the equation is slightly different, because in fluid mechanics, we directly use rho Vd over mu. In fluid mechanics, okay, fluid mechanics, we directly use Reynolds number equal to rho Vd over mu. So this is for pipe. Which pipe the geometry is cylinder. So we are using diameter. But in heat transfer, previously we know that heat transfer already states that Reynolds number, I put it L, so is density times with velocity times with characteristic length over dynamic viscosity. So the characteristic length at this point is x for a flat plate. Okay, flat plate, characteristic length is x. Okay, that's why the equation becomes rho Vx over mu. So as we can see here, there is another form of Reynolds number equation, which is Vx over V. This is the same equation as this, but we have to change it into kinematic viscosity. Again, in fluid mechanics, we already learned that kinematic viscosity is equal to mu over rho. Okay, this is equation for kinematic viscosity. So when we want to change, to when we want to substitute this equation into Reynolds number equation, we have to 1 over kinematic viscosity equal to rho over mu. We can see here rho over mu, and then this is rho over mu. We substitute 1 over V, then the equation becomes Vx over V. So that is Reynolds number equation using kinematic viscosity. Okay, from Reynolds number critical, we can actually determine the critical length of the fluid to the length of the critical length where the laminar flow occurs. Okay, as we can see here in the figure, we have X critical. Normally, at this critical length is laminar flow. Okay, to determine the critical Reynolds number and the critical length, we have to plug in the value of Reynolds number critical into the Reynolds number equation, but you have to change the value to change the notation of X into X critical. Then rearrange your equation, this equation, into X critical equal to 1. X critical equal to 5 times 10 to the power of 5 times with mu over rho V. And from this equation, you can find what is the value of X critical, or the length where the laminar flow occurs. Okay? If you have 10 meter length of flat plate, and then your X critical is 5 meter, then we can imagine that this flow is actually this actually tells us that another 5 meter will be a turbulent flow, and 5 meter will be a critical length where the laminar flow happen. Okay, the actual value of the engineering critical Reynolds number may vary somewhat from 10 to the power of 5 to 3 times 10 to the power of 6. So in this heat transfer for a flat plate, we have to memorize 5 times 10 to the power of 5 to the power of 5 is the critical Reynolds number for a flat plate. Remember, flat plate, 5 times 10 to the power of 5. Okay, as I mentioned before, there are two categories: constant surface temperature, and then the other one is constant surface heat flux. Now we go to the constant surface temperature, where it can be divided into two: local Nusselt number and average Nusselt number. So for the first one, we go to the local Nusselt number. What does it mean by the local Nusselt number? You want to find the local Nusselt number, or you want to find Nusselt number at location X over a flat plate. For example, let's say I have 10 meter length of flat plate, but in the equation, it states specifically at 3 meter length of the flat plate. For example, find the rate of heat transfer at 3 meter. So that means you have to find local Nusselt number at 3 meter, specific. Okay, so in order for us to determine the Nusselt number, or we want to find let's say we want to find rate of heat transfer at 3 meter for a flat plate 10 meters length. So how? Let's take a look on how to do this. Okay, the first step that you need to do is to find a Reynolds number L. So the Reynolds number L, as I told you before, and I've explained before, the equation is density times with velocity times with x divided by mu. Okay, use this equation and determine what is the Reynolds number L. In the second step, compare Reynolds number L with Reynolds number critical for flat plate, which is 5 times 10 to the power of 5. Okay, you need to compare Reynolds number L with Reynolds number critical. If Reynolds number L greater than Reynolds number critical, this flow is turbulent. Okay? Then if Reynolds number L below the Reynolds number critical, this is laminar. Okay? Next, if you already determine these types of flow, you will use the specific equation from local Nusselt number equation, and then you will find Nusselt number by using appropriate equation. Appropriate equation based on step 2. Okay, and then after you find Nusselt number, previously in chapter 3.0 I already told you to memorize this equation. Nusselt number equal to HL over D. Okay, rearrange this equation to get what is H. H is equal to Nusselt number times with diameter over L. Okay, then you already find heat transfer coefficient. And the last step, because in the question it needs you to find rate of heat transfer. Rate of heat transfer. Now you have to substitute into the equations of heat transfer for the convection. Okay, delta T. Delta T is temperature gradient, and it is positive value. So here number 4, substitute into the value for heat transfer coefficient will be substituted into this, and then you will find what is the value of rate of heat transfer. So at this for the local Nusselt number, you must remember you have 10 meter length of flat plate. FP, flat plate, okay? But you need to determine what is the local Nusselt number at 3 meter. Or you want to find what is the rate of heat transfer at 3 meter. You have to plug in the values inside the Reynolds number L with 3 meter. not 10 meter. If you substitute 10 meter, it means that you want to calculate the rate of heat transfer or the Reynolds number for an entire plate. So, but in the equation, in the question, it already mentioned that you need to find what is the rate of heat transfer at 3 meter. And question for local Nusselt number, it is not necessarily to determine what is the rate of heat transfer, but it might change the question to find the heat transfer coefficient at 3 meter. This is just an example steps for you to determine what is the rate of heat transfer at 3 meter for 10 meter length of flat plate. Okay, this is the equation that I've told you. When you determine the Reynolds number length, L is much more greater than Reynolds number critical, it will fall under turbulent flow, then you directly use this equation. Okay, substitute all the values that you've already calculated before into this equation to find what is the Nusselt number. And then if Reynolds number length L is lower than Reynolds number critical, you have to substitute into laminar flow equation. Okay, in this figure, it shows that the heat transfer coefficient has different values when different value when the x coordinate increases, and the heat transfer coefficient reach its maximum when it falls into turbulent flow regime. Okay, in laminar flow it will decrease because the heat transfer under laminar flow it is not effective as in turbulent flow. Okay, so next is average Nusselt number. So when the question asks you to find the Nusselt number or to find the rate of heat transfer for entire plate, okay, entire plate. So this means that you need to find what is the average Nusselt number, then you have to find heat transfer coefficient, then you plug in the values of heat transfer coefficient into rate of heat transfer to determine what is Q dot. Okay, the steps are the same as before. First, you have to determine what is the Reynolds number L by using the equation rho V x over mu. Okay, at this point, as we can see here, previously we need to determine the local Nusselt number. Even there is 10 meter length of flat plate, and the question needs you to find Nusselt number at 3 meter. You have to substitute x value for 3 meter. But at this for the average Nusselt number, you have to substitute 10 meter because entire flat plate. So the x value here will be 10 meter. Okay, number 2, you have to compare. So compare Reynolds number L with Reynolds number critical. So if turbulent, okay, if Reynolds number L much more greater than Reynolds number critical, this is turbulent. Okay. If Reynolds number L lower than Reynolds number critical, this is laminar flow. Okay. Third step, you have to find or calculate Nusselt number using appropriate equation. Okay, appropriate equation. This equation depends on number 2. Okay, step number 4, find H by using Nusselt number equal to HL over D. So H equal to Nusselt number times with D over L. Okay, last step, because I've mentioned before that the question might need you to find what is the rate of heat transfer. So substitute into Q dot equal to HAS delta T. This chapter falls under convection heat transfer mechanism. Therefore, the equation used is convection. This is not conduction, this is convection heat transfer mechanism. That's why the equation that we use in order for you to determine what is the rate of heat transfer comes from convection equation. Okay, that is the previous step for the local Nusselt number, same as what in the local Nusselt number. But have you ever noticed that, as I told you before, that in the flat plate, okay, this is the figure, we have two different, this is lamina, two different region occurs over a flat plate, right? Which are lamina and turbulent flow. So what will happen if lamina and turbulent flow are significant? Okay, let's say your flat plate is 10 meter, and after you calculate, okay, you found that X critical, you calculate X critical, you found that X critical is 5 meter. Okay, about half of the flat plate is laminar flow. Then we cannot disregard laminar flow in our calculation. Therefore, okay, there is another equation that needs to be used. This equation for laminar and turbulence flow are significant. So in the books, they are always, the book authors always use this equation. Why? Because if you use this equation, if your flow is turbulent flow, then this equation will be reduced and it will same as turbulent flow equation. But if the equation, the questions and the calculation is much more to the laminar flow, then this equation will turn into laminar flow equation. Okay, in the books always use this equation because we never know on how much laminar flow or how much percentage of length needs to be considered before it can be omitted. Okay, before it can be disregarded, which means we never know at what length of the laminar flow or at what length of the critical Reynolds critical length needs to be considered in our calculation. Therefore, it is good for you to use this equation, because this equation, if If your flows is a turbulent flow, then it will reduce into turbulent flow equation and vice versa. But in your final exam, normally they will use either laminar or turbulent flow. But in real situation, you have to use this equation in order for you to determine what is the value for Nusselt number for a laminar and turbulent flow. Because we are considering entire flat plate, and an entire flat plate have two different flow regime, laminar and turbulent flow. Okay, and the last but not least, okay, for the flat plate is uniform heat flux. So when a flat plate is subjected to uniform heat flux instead of uniform temperature, so uniform temperature is local Nusselt number and average Nusselt number. And at this point, remember, I've told you previously that there is two conditions where you need constant surface heat temperature and constant uniform heat flux. At this point, constant uniform heat flux. So the local Nusselt number is given by the steps are same as before. One, you have to determine what is the Reynolds number L, okay, by using the equation rho Vx over mu. And then second, you have to compare with Reynolds number critical, 5 times 10 to the power of 5. Then you determine whether that flows is laminar or turbulent flow. After you determine, for example, laminar flow, then directly use laminar flow equation here. So directly use So directly use the equations of equation for laminar flow. Okay, here laminar flow equation. Okay, if your Reynolds number L is much more greater than Reynolds number critical, then you use turbulent flow equation. So what is uniform heat flux? So let's say we have flat plate. Okay, we have another heat source comes from outside. Okay, another heat source being penetrate into the flat plate. So this is heat flux. Okay, heat flux, uniform heat flux. Maybe uniform heat flux comes from electrical heater. For example, electrical heater is one of the constant or uniform heat flux. Okay, we can actually normally questions that give you uniform heat flux will not give you this temperature Ts, but they will give you T infinity. So in order for you to determine what is Ts, so here Q dot is heat flux is equal to Q divided by area. So heat flux unit for Q dot is watt per meter square, and unit for Q is watt, area is meter square. So Q over A is watt per meter square, equivalent to left hand side Q dot. So you have to rearrange this equation equivalent to Q dot A. And this is Q dot because rate. Q dot, the equation is H ES delta T, okay, equal to Q dot A. Okay, let's say the Ts much more greater than T infinity because this is where the heat flux, uniform heat flux comes from, and then Ts much more greater, the temperature much more greater than Q, then the heat would be from Ts to T infinity. So this is Q dot. Okay, rearrange this equation. So from here, HAS, so we have Ts minus T infinity. Okay, equal to Q dot A. Rearrange the equation, Ts minus T infinity equal to Q dot A over HAS. Oops. Okay, HAS. So Ts, so you want to find what is Ts, equal to Q dot A over HAS minus plus T infinity. The area here is the same as AS, so we can cancel out. So therefore, this equation becomes Ts equal to Q dot over H plus T infinity. Actions on the equation of Nusselt number. Previously, I've made a mistake. I'm really sorry because I wrongly wrote down the equation for Nusselt number. So as I mentioned before, the Nusselt number is equal to HL over D. Okay, this is totally wrong. Wrong equation. Wrong equation. So the real equation, the correct equation, okay, for correct equation for Nusselt number is Nusselt number equal to HL over K. By rearranging this equation, you to get heat transfer coefficient, you will get this equation. So Nusselt number times with K over L. So K is thermal conductivity. Thermal conductivity. L is length of the flat plate. And Nusselt number is Nusselt number. Therefore, by using this equation, you may find heat transfer coefficient. Okay.